This video shows the simulation and working model of floating point multiplier. So the floating point number representation has sign bit, mantissa bits and the exponent bits. The number of bits required for each part depends on the precision required. Here we are considering the single precision floating point number representation, which has 1 sign bit, 8 exponent bits and 23 mantissa bits with 1 hidden bit. So float underscore mult is the module name of this floating point multiplier, wherein we have the mantissa resolution as 23 and exponent resolution as 8. And A and B are the inputs, each of 32 bits. So 0 to 31 is the 32 bits and mult is the output. So the procedure for the floating point multiplication is that we need to multiply the mantissas along with the uh, proper hidden bit representation, and then we also need to do the exponent normalization or exponent equalization. So now multiplier underscore signed is the module which does the integer multiplication, a simple integer multiplication which is implemented using the value string multiplier, and recursive signed is for the integer addition. The proper biasing of the exponent of minus 127 should be taken care of. There are two procedures where you can subtract 127 from each of the exponent and finally add 127, or we can add off the two exponents and finally subtract the 127. So now let's look into the test bench of the floating point multiplier. I have included all the required submodules over here, and the top module instantiation is given here. This is the design and under the test. These are the inputs considered. A, Z and B, Z are the hidden bits of the mantissas of A and B. So over 32 bits of floating point representation, 31st bit was taken as a sign, and then the 8 bits were taken as exponent, and other 23 bits were taken as mantissa. So these are the different sort of inputs that were given in binary, and next we'll have the value change dump file, and we'll monitor the outputs, and finally we will look into the waveform. So now let us simulate this test bench. So for that we'll go into the same folder where this test bench is located. We'll use a tool called icaris Verilog, and the command for this is given here. -G 2001 gives the version number which is to be used. So this is the test bench name. Since I have included all the submodules over here, there is no requirement to be included in the command window. So vvp_a.out is the command for viewing the outputs. Here if we can this is shown in the binary for clear segregation of exponent bits, mantissa bits of inputs as well as outputs. So these are the sign bits and these are the exponent bits of the inputs, and this is the exponent bit of the output and exponent bit mantissa bit of the output and exponent bit of the output. So now let us look into the waveform. The tool we use is GTK wave. The command is as follows, and we'll be calling this value change dump file. So now let us take all the inputs. Yes, the first set of inputs that I have given were 18.0 and 9.5, which should result in 177. So let us check this output. 432B40 is 171. So yes, the first set of output was correct, and the second set of inputs that I've given were 4.5 and 2.2, which should result in 9.9. So let us check this. 411E46s. This is 9.8 all nines, which is equal to 9.9. So the third set of inputs that I have given were 22 and 7.2, which should result in 158.4. So the third set of output is 431E46. This is all in hexadecimal. I am just trying to convert it into decimal. So 158.4. So the correctness of the output is checked over here. Since there is hexadecimal representation over here, we have verified that with the floating point representation using this online converter. Thank you.